In this second video for section 6.4, we're going to show how to use calculus techniques to calculate the surface area that we get when we revolve a function about either the x-axis or the y-axis. So let's start with a couple of pictures to illustrate the region whose surface area we're trying to find. So we've got this function y equals x cubed, which is right here on the interval 1, 2. We're revolving at 360 degrees about the x-axis, and when we do that, we get a figure that looks like this. There's a cutaway in it, so we don't see the whole thing, but we're trying to find the area of this skin, of this surface here, which looks like a cone. We're not finding its volume, we're just finding the area of the surface of this cone. So let's put a couple more pictures up here to show how we use calculus methods to find the area of this surface. So we're going to take a small slice of this surface area, and that is going to look like a ribbon, like this ribbon here. And that ribbon is sort of blown up in this drawing. The ribbon has an inner radius on this side, which is smaller than its outer radius, which is on this side. This x value here is going to be x sub I minus 1, a generalized x value. This x value here is going to be f of xi, so this outer radius is going to be the value of the function at that x value, and this inner radius is going to be the value of the function at that x value. And the way we determine this surface area is to calculate what's called the frustum of a cone. The frustum of a cone is determined from this cross section here. So what we're going to do is we're going to take the slant amount here and then add this outer radius and this inner radius using this formula that we'll show on the next blackboard, and that's going to give the area of this, which is the cross section of a cone. So we've got all the parts here written out. That slant line length is this same length that we found using the arc length formula in the previous video. The frustum of a cone, the area of the frustum of a cone, is calculated by pi times this slant height, which is this, times the inner radius plus the outer radius. And those inner radius and outer radius were what? F of xi minus 1 and f of xi. The dl was this formula here. And actually the dl formula should have a delta xi multiplying it here. So the if we break up the parts, right, here's the pi, here's the slant height, and here is the sum of the inner and the outer radius. So and then we're summing each one of these is going to give, each one of these here is going to give the surface area of one of these ribbons, and that error is going to get less and less as delta x sub I goes to 0, and we're adding all those up. Remember, there's a little bit of error here because when we use this slant height right here, that is an approximation because the figure is actually curved, right, like this, and so the actual heights are like this. But as delta xi goes to 0, we get the error going to 0. So we're going to use this formula right here, and we're going to let delta xi go to 0, which is going to turn the summation into an integral, and it's going to turn the delta xi into a dx. So let's do that on the next blackboard. And so we have this surface area formula, which you see is very similar to the arc length formula, right? This part right here was exactly in the arc length formula, and the part that's new is this 2 pi f of x part. So let's apply this to example 4. So example 4, we are revolving the function f of x equals the square root of 4x plus 1 about the x-axis on the interval 0, 1. So the first thing that we need to do is take the derivative of f of x and then square it. So we're taking the derivative of f of x, bring the power down, reduce it by 1, multiply by the derivative of the inside, which gives us this, and then let's write that in simplified form with the 4 canceling the 2 and bringing the minus 1/2 down into the denominator as a radical. And then we're going to need to square f prime of x, so let's do that. And so that gives us this 4 over 4x plus 1 that we're going to put into the formula where f prime of x is. So let's take a look at where we are on the next blackboard. So here is the square root of f prime of x plus 1, and this part right here is the 2 pi f of x part. What we want to do, it looks like we're kind of stuck here, but it turns out that if we get a common denominator between these two terms here and write it instead of as being a radical like this as the square root of a over the square root of b, we can simplify what's under the integral sign a great deal. So let's calculate those steps. So 2 pi, 0 to 1, no change here, and under this radical we're going to get the common denominator of 4x plus 1, and this 4 doesn't change, but this 1 changes to 4x plus 1, so this radical becomes the square root of 4x plus 5 over 4x plus 1, and that's the same as the square root of 4x plus 5 over the square root of 4x plus 1. So let's use this form and see that that helps us out a great deal. So we've put everything together in this revised form over here, and that allows us to calculate, or to cancel this radical and this radical, and when we do that, we simply have this remaining. So we're going to pick up with this on the next blackboard. So to resolve this integral, we're going to let, actually there's a mistake here, let me fix it. So we're going to let u equal 4x plus 5, so that we are taking the integral of the square root of u. And so we note that du is 4 dx, or dx is du over 4. And these limits of integration here are in the variable x. To get the u limits of integration, If x is 0 and we plug 0 in here, we get u is 5. So that's when x is 0, and if x is the other limit 1, then u is 9. So our integral in the u variable is what? 2 pi. The new limits of integration are 5 to 9. It's u to the 1/2 du, but we've got an over 4 here from dx being du over 4. And so that's what, pi over 2. We integrate u to the 1/2 and get 2/3 u to the 3/2 evaluated between 5 and 9. These 2's right here cancel out, and so we get pi over 3 times 9 to the 3/2, which is square root of 9 cubed, which is 27, and then minus 5 to the 3/2, which is 5 square roots of 5. And in your textbook you see that that is the same as, or approximately the same as, 16.566. And that's on page 128 of your textbook, where this example is wrapped up. So let's do one more example, which picks up with the method we did for the arc length problem, where we had to complete the square and factor, and where we had a minus 1/2 that turned to a plus 1/2. So in this example 5, we are revolving this function, f of x equals x to the 4th over 4 plus x to the minus 2 over 8, the same function we had before back in example 2, was it, of this section? And so we're going to be able to use some of the information they already have. We're revolving this about the x-axis on the interval 1 to 2. And so we already have that from before, that the square root of f prime of x squared plus 1 from example 2 is x cubed plus x to the minus 3 over 4. So when we plug this into our surface area formula, let's see what we get. So the 1 plus f prime of x squared square root, remember it, oops, I had a mistake here, hold on a second. No, that's right, we're going to use this, and so the 1 plus f prime of x squared square root is the same as we had before. The f of x, we're just plugging in the function. The 2 pi is out front. The book shows what it's like when we multiply the terms out and collect like terms, so let's go to that result. So that gives us this, and then you can see at the bottom of page 128 on your book that when you do these computations, you get approximately 51.882. But that's an integral that we can compute exactly. It's actually also what, well, you can see the computations on the bottom of page 128. So wrapping up, let's take one more look at our arc length formula. And see that it's very similar to the, our surface area formula. It's very similar to the arc length formula. This part right here is exactly what we use in the arc length formula, and then we just add in the function itself and a 2 pi out front. So you can think of this part right here as sort of like a circumference times a length, even though it's a little bit more complicated than that, how it pieces together with the frustum of a cone area. But That's probably a good way to remember it, is circumference times length. Okay, so that, with these two examples, concludes this video on the second part of section 6.4, surface area.